So in this video, we're going to look at lines and planes in 3D. Basically, we're going to be looking at equations, in fact, of lines and planes in 3 dimensions. So we'll start with the first looking at the equation of a line. It's best to start with what we're really familiar with. As you all know quite well, we all know quite well y equals mx plus c at this stage, which is the equation of the line. One of the first, if not the first, equation versus geometry situation that a student comes across, or any one of us comes across, is when we draw something and then we write an equation that represents that drawing, and that is the equation of the line. Now, in the equation of the line, the most interesting and important thing is the slope of the line. The slope of the line is quite important. It tells us about the orientation of the line. Essentially, as you know, in 2 dimensions, the line basically represents, it's the angle with the x-axis. So in this way, or this, or so on. And by, in fact, just knowing one point on the line, any point on the line and the slope of the line, we can find the equation of the line. Now, this concept, it becomes much more complex when we look at the same situation only in 3D. So in 3 dimensions, this being our y-axis, the x, and the z-axis. So in this situation, what's going on is basically the line is no longer, it's very difficult to now just concentrate on the angle or the slope of the line. It's rather difficult because if, suppose, for the sake of argument, this is the line, suppose this is the line, and that we want to get the equation of this line, for instance. The issue is what angle and with what axis, and it's very complicated. And as you move the line along, the number of angles becomes significant, and it becomes next to impossible, if not very complicated at least, to try to use this angle idea or slope idea. So another very easy way to actually overcome this is, in fact, by looking at the slope of a line. So let me just rub this out for a second and go back here, and let's just talk about another idea that might be more helpful to us. So let me draw, for instance, a line, any line, okay, that we're interested in. And let's say that here P, let's say P0 is a point on this line, okay? And let's say P0 has coordinates x0, y0, and z0, okay? So this is the point P0 on this line. Now, not only is this a point on the line, but it is also a vector. I'll come to that in a second, but before that, let me try to go back to this slope idea. So since the slope is rather difficult, what other possibility is there? Well, one other possibility is to say that the line that we are interested in, this line L, in fact, happens to be parallel to this vector. Let's call it V, okay? So V is a vector, and let's say its components or its definition is ABC, okay? So V is some vector that is parallel to this line. Now, rather than saying parallel to this line, we can say that, for instance, we can state a requirement like, okay, given a point P0 on a line, the line being identified as one that is parallel to the vector V, find the equation of the line. The fact is that the idea of the line being parallel to a vector has much more uniqueness in it. Now, it's a little difficult for me to show you this here, but for instance, if this vector V or a different vector was facing this way, for instance, okay, let's call it V1. Now, the line that would be parallel to it would be something like, for instance, this line perhaps. Okay, now as you can see, look at the contrast between just these 2 lines. Let's call this L1. You'll see that it's drastically changed. However, what is very interesting is the only information we need to have this orientation of the line is the vector V, or the vector V1 in the second example. So here is a very useful in fact, tool for us to look at and explore how we can, in fact, get to the equation of this line L. Okay, so here's the line L, and this is the vector V, and we want to, in fact, find the equation of this line. Let us choose an arbitrary point P on this line, and let's say that P has coordinates X, Y, and Z. Okay, now just a few minutes ago, I made a comment that P0 is not just, in fact, a point, but it can also, just like any point, can also be thought as the vector, say, let's call it R0. So in other words, what I'm saying is R0 is the vector with coordinates x0, y0, z0, right? And the vector here, this is also a vector, and let's call this the vector R. And the vector R has, in fact, coordinates x, y, and z. Now, my question to you is, let us look at this particular vector here. If we look at this vector here, this is the vector P0P. So P0P is what vector? Well, we know that we can very easily calculate the vector that is between any 2 points by simply taking the difference between. This means this is x minus x0, y minus y0, and z minus z0. So these are the coordinates of this vector. Now, what is this in fact? You will notice that that is the same as r minus r0 in fact. So basically we have this vector P0P or r minus r0. Now, what is the relationship between P0P and the vector V? We know that they are both parallel. Two vectors that are parallel, we know there is a relationship, a very simple idea, which I will try to show you here. Let me just clear up some space here. Okay. For instance, here's U, and this is suppose V. Let's make V a little double the size of U. Then what we do know is that U, okay, is 2U, in fact, equals V, for instance. In other words, two vectors that are parallel, in fact, are related to each other by the equality symbol, by the difference of a factor of a scalar. So you see this is a scalar value here. So in other words, any two vectors, U and V, could be just equated to each other by the factor k. So two vectors are parallel, say U and V are parallel, then U is equal to k times V. So here, if we return to our situation, this means now since P0P is parallel to V, it means that R minus R0 or P0P can be said to be equal to k times some scalar k, or I'm sorry, let's not use k, let's use the scalar t times the vector V. So in other words, R minus R0 is equal to TV, and here you have a very interesting relationship, which means that R, rearranging, is simply R0 plus T times V. Now this is a very important result. This in fact is the vector equation, so it's known as the vector equation of a line. And I'm not going to say 3D only because, in fact, whereas I've done the example for 3D, we can easily remove the z coordinate, and the same thing applies even in the 2 dimensions. Okay. Now, in component form, so R on the left-hand side would be x, y, z, and that's in fact equal to R0, the R0, so R0 is x0, y0, z0, plus t times a, b, c. Now, we also know very well that two vectors are equal if every component of that vector is in fact equal. So this means that x must be equal to x0 plus t a. Y at the same time must also be equal to plus tb, and z is equal to z0 plus tc. these are called the parametric, okay, and the particular one I have here now is in fact in 3D. So this is the process is called parametrizing. So anyway, parametrizing a line in 3 space or 2 space, either way. Just remove the z coordinate and you have it in 3 space as well, 2 space, sorry. Now, so these are called the parametric equations. I want to show you just one more thing here, which is very quickly. If we go from this representation, this last representation, and you can see that from this equation, I can get, in fact, I can rewrite this equation as t equals x minus x0 over a, and I can get from this one that t is equal to y minus y0 over b, and from this third one that t is equal to z minus z0 over c. Now, all of these 3 equations, or these 3 relationships, have one thing in common, and that's the t, which means that what essentially boils down to saying is that x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. Now, these are called symmetric, okay, or symmetric equations representing a line in 3 space. So that basically covers the equation of the line. So there are 3 different representations that we've looked at. This one here, the vector equation of a line. Okay, we've looked at the vector equation of the line. We've looked at the parametric equations of a line, and we've looked at symmetric equations of a line. So let's move on now and look at a similar idea can be explored in when we look at planes, in fact. So say we want to find the equation of a line through the point 2, 3, 4 and parallel to the vector v, which is 1, minus 1, minus 3. Okay, so this is quite easy to do. In fact, we know that if the vector equation of this line is going to be r is equal to 2, 3, 4, okay, plus t times 1 minus 1 minus 3. And the parametrization of the equation of this line will be, in fact, x is equal to 2 plus t, y is equal to 3 minus t, and z is equal to 4 minus 3t. So those would be the parametrized equations. Another different question could be, for instance, another possibility is someone can give us 2 points. For instance, 1, 1, 1 and the point 3, 3, 3. Now if we have these 2 points, let's say A and B, and we're asked what is the equation of the line that these 2 points lie on. Well, let's just think about it this way. If we had any 2 points lying on a line, say A and B, okay, clearly if we could find this vector, which is very easy, in fact it's the vector AB. So the vector AB in this case is 2, 2, 2, and this vector happens to be parallel to this line L. So therefore it's our V, in other words. So therefore the equation of the line simply becomes r is equal to 1, 1, 1. Choose any one of the 2 points. You can just as easily choose a 3, 3, 3 if you like, no problem. Plus t times 2, 2, 2. And this would be the equation, the vector equation of this line. And similarly, you can get the parametrized form as well.